This is our 26th physics lesson. We're going to look at momentum and impulse. We're going to look at the momentum equation. We're going to look at the impulse equation. We'll solve for variables in each of those. We'll look at how increasing the time of impulse decreases the force of impulse. We'll understand how impulse changes momentum and look at that equation and solve for different variables with that as well. So momentum, the symbol is P, the variable you'll see in an equation. Often you'll see a P that looks like that. As an object's moving inertia. So we'll see that the equation mass times velocity is equal to momentum. It's moving, its velocity, and its mass is its normal inertia. Well, it's going to be moving inertia because it has a velocity that's making it move. So to have momentum, you must have mass, you must have a velocity of some sort. And the unit comes from mass kilograms and velocity meters per second. It doesn't have its own unit, so it'd be kilograms times meters per second. And the variables, fill in the variables if you're following my notes. If not, it's good just to get these down somewhere. Momentum, these are the variables are what you find in an equation. So P is for momentum, mass is the M, velocity is V, impulse is J, time is T. Whereas the unit abbreviation, this is what you put after the number when you're done solving for one of these. For momentum, it would be something kilograms times meters per second. For mass, it would be something kilograms. For velocity, something meters per second. For impulse, it would be something newtons per second, and for time, it would be something seconds. Momentum is directly related to mass. The larger the mass, moving at the same speed, so this goes up, that goes up. So we can see a 5 kilogram car going 10 meters per second, multiply those two together to get momentum, you get 50 kilograms times meters per second. If you have the bigger car over here, 35 kilogram car going 10 meters per second, same speed, the velocity is same, the momentum changed because of the mass. So multiply 35 times 10, you get 350 kilograms times meters per second. So what happens to momentum of the mass of a moving object is increased? It's going to increase. Once again, going with the momentum equals mass times velocity equation. If mass goes up, momentum goes up as a result. How much more momentum does a 35 kilogram object have than a 5 kilogram object? So for this, you have to set up a ratio. And I should have said that it was moving, because if it's not moving, then you don't have momentum in the first place, so it won't matter. But if it was moving, 35 is divided by 5. 35 is 7 times. So just take the bigger number, divide by the smaller number, or take the initial number, put that on the bottom, take the new number, put it on top, and take that and find out how many times different it is, and we get 7 times different the mass. It's asking you for how much the momentum changes. So the equivalent of momentum is mass times velocity. So the equivalent of having P is mv. And we can just put that over the before scenario, and we're going to do ratios. Anything that doesn't change is going to get a 1. So before, everything was 1s. But the only thing that changed is that the mass was 7 times the original after in the what we're comparing it to. Or with our new one, where we compare it from. And so our answer is our new value, if we had a 35 kilogram car instead of 5 kilogram car, would be 7 times whatever the momentum was before. I don't know what it is, but if I knew it, I would just multiply it by 7. Momentum is directly related to velocity. The larger the velocity of the same mass, car, automobile, or whatever, the larger the momentum. First of all, you need to be moving in the first place. So this guy right here is not going to have a momentum, because anything times 0, or once again, P equals mv right there. Anything times 0 would be 0. But as the car starts moving, so like right here, you have a 15 kilogram car going 10 meters per second. It's going to have a little more momentum. It's going to have 15 times 10, or 150 kilograms times meters per second of momentum. And then this one right here going 20 meters per second is going to have 20 times the 15, or 300 kilograms times meters per second. So how much momentum does a 1,575 kilogram Lamborghini Aventador have at its top speed of 97 meters per second? So let's just straight up write down the variables. It's asking you for momentum, they give you mass, they give you velocity, and you're just going to multiply those together in that equation, and you get 152,775 kilograms times meters per second, and we can put that in scientific notation as 1.5 times 10 to the 5th kilograms times meters per second. How much more momentum does an object have when its velocity is tripled? So it's asking you for momentum, and so this equation, this is the equivalent. We can put the equivalent over the equivalent, set up an after versus before scenario. Everything's the same before. The mass was the same. It doesn't say anything about the mass, but the velocity is 3 times, so our answer is 3 times its original value. Change of momentum and impulse. So an object changes momentum when velocity is changed. Take a look at the ball coming in. It changes momentum because it's going backwards after the ball's hit. And the momentum equations you can use is the change in momentum equals mass times change in velocity. So before we were just saying what was the momentum of an object at the moment. Well, now we're asked for how much is it changed versus before. So we're going to have a changing velocity going on. And depending on how the question's asked, if they say the change in velocity was 5 meters per second, well, we would use this version of it. But if they say the change in, or the final velocity, what is the final velocity when the initial velocity was, let's say, 6 kilogram, was a 15 kilogram object, its change in momentum was blah, 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 blah. Well, we would go to this equation. So the givens list is going to help you choose which equations and where to go from there. You also have to account for direction. If this is going up to the right, I always say to the right is positive, and therefore to the left is negative. When you have a change in direction, you have to do that. If you don't have a change in direction, you can just say forward. But here we can definitely see a changing direction. So we would say it's initially coming in with a positive velocity, it leaves with a negative velocity, and then we would plug those numbers into the equation. So let's look closer at some of those. What's the change in momentum of a 0.145 kilogram baseball traveling at 44 meters per second forward when hit back at negative or at 60 meters per second? So back is going to make that negative. We have our variables. What's the change in momentum? So there's your change in P instead of P. It didn't say what's your momentum. It says what's your change in momentum. And so that gives me this right here, this change in momentum. They'll give you a mass, they give you initial velocity, and they give you a final velocity, once again taking into account back or the negative. And this is the equation this would lead us to. Plug in our values, and when we plug in our values, and just watch out here, this is VF, which was a negative value, minus a positive value, which makes it a minus 2. So these is going to be minus and minus. They're going to be pretty much added in both negative, but when you get your answer, when you type these in the calculator or do it in your head if you're really good at this, you're going to get negative 15 kilograms times meters per second as your momentum. An impulse is a force applied for time, so we're going into the next section, and it results in the change in momentum. If you apply a force, if you hit something with a force and it touches a baseball for a fraction of a second, you're going to change the direction that object's going. You're going to change its momentum. So the basic equation, there's your J for impulse, there's your variable in the equation, and that's equal to force applied over time, or times time. And so the unit doesn't have its own unit either. The force unit, newtons, the time unit, second. So it's newtons times second as a unit after you would type it right in a number. And so a bat would create an impulse force for a fraction of a second, changing the velocity of the baseball. So it's going to change its momentum. Let's look at some equations here. How much force is applied during a 0.3 second, 210 Newton per second impulse? So how much force is applied during this time with this impulse? And so we're going to have the impulse equation, but we're going to solve for force. So we're going to divide out the time, and we get force is equal to impulse over time. Plug in our numbers, and we get a force of 700 newtons. How much different is the force when padding increases the time of impulse 3 times? So how much is the force different when padding increases the force 3 times? We're going to have to find the equivalent. In order to find the equivalent, we have to go ahead and rearrange this for force, and you kind of saw that initially. So rearrange this for force, you divide by time, divide by time. The equivalent of force is impulse over time. So we're going to put impulse over time over itself, and we're going to plug in ones for everything before. And we're going to have so the before is right here, the after is right here. And the only thing that's going to change now is that the time of impulse increases 3 times. So the time, this is the only one that changes. Everything else is all the same. And we're going to get an answer of 1/3 times the original. So if it was 100 before, it would be 33.3333 afterwards. Whatever you would know before. If you don't know it before, you can just give a ratio, a relative value. You don't know what it actually was. It's 1.3, 1/3 times. Impulse is equal to an object change in momentum. So let's take a look. Impulse is that equation, and change in momentum is that equation. And when we set it up so that impulse equals change in momentum, we're going to go ahead and we're going to expand that and make Ft equals the mv squared. So impulse equals the change in momentum. So this is impulse not expanded. It's change in momentum expanded. Here, this is just the same version, but we're just going to go ahead and we're going to expand J into Ft, which makes up J. And so we're just going to have a bunch of different versions depending on the information we're given. And if we're given final initial velocities, we're going to want to expand that out even more into final initial velocities right here. How much force is required to stop a 0.145 kilogram baseball traveling at 44 meters per second in 0.2020 seconds? So the given us is going to be very important to pick the right equation, all these equations right here. So force is what we're solving for. We're given a mass, we're given initial velocity, we are given a final velocity, so that's going to lead us, and a time, and so that's going to lead us to this equation right here. So you rearrange it. So force is equal to take all this, divide time out from both sides. When you divide time out from both sides, you get this. Then you can start plugging in values. When you plug in values, you should get an answer of negative 319 newtons or backwards 319 newtons. The unit for impulse equals the unit for change in momentum. Just in case you're wondering, okay, so how are they equal, but yet they have different units? Well, this newtons per second is actually made up of kilograms times meters per second. And let's just take a look and see how that works. So we have the unit for impulse, newtons times seconds. Well, a newton is derived from, remember, force. Newton is force, which equals mass times acceleration. It's derived from mass, which is kilograms, acceleration, which is meters per second squared. And then if we just multiply that by, so that's what a newton is, and multiplied by seconds, that's the same thing. Well, when we take that and we can divide out this second and one of those seconds, so we get kilograms times meters per second, which is exactly what the unit for momentum was. So it's exactly the same thing. And the common thing is to do is if you're solving for momentum, you're going to give an answer in kilograms times meters per second. If you're solving for impulse, you're going to give an answer as newtons per second. But they mean the same thing. So either of them really would truly be correct. Cushioning increases the time, decreasing the force of impact. When you have your beautiful car crushed in an accident, it actually could save your life. It could stop you from being injured because it increases the amount of time, and therefore it decreases the amount of force being felt, because what's not changing, you have the same car stopping, the same mass of cars, so that momentum is the same. So momentum is going to be, the change of momentum is going to be the same. The impulse is going to be the same because the impulse is equal to change in momentum. So what you're going to have to do, you're going to break down this. So the mass and velocity and change in velocity, this is going to be the same. The velocity, change in velocity is from 15 to 0. The mass is the same. If I can go ahead, that's not distance, that should be time. If I can go ahead and increase the amount of time, that's going to therefore decrease the amount of force because this is going to be unchanged. And so if padding, any sort of cushioning that takes more time to stop something, would decrease the amount of force for the same change in momentum. So both have the same change in momentum, and that's what I explained before. That's kind of what I was talking about. So just note, if you have more time, you're going to have less force when you have the same change in momentum or the same impulse. How can padding or the crushing of a car on impact keep a person safe? Well, that's just what I said earlier. Crushing or padding increases the time of impulse, which decreases the force. So here's a problem set. Make sure that you've done the problem set before you check your answers. We're just going to go quickly through this. Once you're done with the problem set, just to check your answers so you can see the work if you didn't know why you got something wrong. So the first one, how many times different is the momentum of a truck that has double the mass and double the velocity of the car? Is going to be the rule, the ratio law, rule of ones, setting up a ratio. Double the mass, double the velocity, keep everything before the same because it was whatever it was. What it is, it was what it was, and we get 4 times whatever it was. How much momentum does a 2 kilogram toy car going 3.25 meters per second have? Well, this is just a straight up momentum equation. It's not asking you for a change or anything. You just multiply the mass times velocity. So you get 6.5 kilograms times meters per second. What's the mass of a bicycle that has 108 newton meters of momentum and a speed of 12 meters per second? So there's our variables we're given. We have our equation. We're going to have to divide. We get mass alone. So we're going to get mass equals momentum of velocity, and we get an answer of 9 kilograms as our answer. How much force is applied in 0.5 seconds if the impulse is 18.2 newtons per second? So these are this is the information they gave us. Rearrange it for force, and we get an answer of 700 newtons as our final answer. How much force is required to stop a 1,200 kilogram car? So watch out, stop. It's going to have a VF of 0, traveling at 8.5 meters per second in 3 seconds. So this is all information I get from this problem. And so when I get my answer, I'm going to get negative 3,400 newtons or 3,400 newtons backwards to stop the object. How many times different is the force at the time of impulse is decreased? So this is not good if you're trying to protect yourself. The impulse is decreased by half. The time of impulse is decreased by half. So rearrange it for force. The equivalent of force is impulse over time. Put it over itself. And when it becomes 1/2 of what it was, the actual 1 over 0.5 ends up being 2 times the original value. So the force, you're going to feel twice as much of the force and therefore the hurt as a result of the force. What's the final velocity of a 0.152 kilogram t-ball that has a force of 10 newtons applied for 0.18 seconds starting from rest? So here's all the information they gave you. And when we rearrange this, so just taking a look at the math, we're asked for velocity, find velocity. We're going to have to first divide out the mass to get rid of mass, and then we can do, so we have to do the multiplication part, division to get rid of the multiplication before we do anything else. And then we can go ahead, and we can add the VI from both sides. And now we have final velocity equals that. So we can plug in our values, and when you get your answers, you should get 11.84 meters per second. What's the final velocity of a 0.145 kilogram baseball when a force of 25 newtons is applied backwards for 0.15 seconds starting from 10? So it has a velocity this time. It's not 0 this time. Same mass, same equation, except this time we're going to have that the initial of 10 in there. And so when you do the math, you end up getting negative 15.86 meters per second or 15.86 meters per second